Hello everyone! Welcome to the OneClass channel. My name is Millan and I'm a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and university or college levels. If you are interested in getting help with your homework or if you're interested in getting some tutoring, check out the links in the description below. Cool, so I'm going to switch my screen real fast and we can get this physics party started. Cool. So the first question that we got on the menu today is actually kind of like 3 questions broken down, but no worries, we can still address them properly. So the first question is asking us, well, it gives us this situation where we have 2 particles, each with a charge of positive q. We don't really know what q is numerically, but we know it's just going to be q, and we can just, we can go about this and proceed just knowing q is a variable and is positive. So 2 particles, each with a charge of positive q, are located on opposite corners of a square. And the side of the square is d. So the question is asking, which is the direction of the net electric field at the point P, which is right here. Okay, so let's actually draw out this situation. Conveniently, I can draw out a nice square like this. Kind of represent this situation, looks good. Okay, so we know that here we have charge plus q. And here we also have a plus q. Nice and straightforward. Okay, so this is a square, so we can say that all sides are like this, and this distance right here is d. Okay, so what we're looking for is the net electric field, or the direction of the net electric field at this point P. Okay, so let's think about this for a second. Electric fields. Whoops, spelling is not my thing. Electric fields. Their direction is, the direction that an electric field is going to point is the direction where a hypothetical positive particle would be pushed. So direction is where a positive particle would be pushed. So positive charges are repulsive. They have outwards electric fields. So positive is like this in terms of the E field. And negative charges have incoming, because opposites attract. So a hypothetical positive particle would be attracted towards a negative charge. Okay? Cool. And that would be the E field here. So attraction. Nope. This is repulsion. This is attraction. Okay, so now let's, given this that we know about electric fields, let's apply this to the square situation that we have right now. Okay, so you see the 2 Q's on the corner. The first one, it's a positive charge. That means the electric field is radiating outwards from itself. Okay, so let's take a look at the top left corner here. If we're going outwards, well, P is really just going to feel like it's straight downwards push from here, right? Right, because this is what the electric field is going to look like for here. And P is just going to feel it straight downwards because, well, given the position of P relative to that, that's just kind of what it would be like. And for the bottom right corner Q, it's giving out an electric field in all directions in the same way, and it's all outwards because it's a positive charge. And what point P is going to experience is just the electric field towards the left, pointing towards the left. Okay, so that's the situation that's going to be happening here. And what's really going on, let's write this in purple, the combination of red and blue. So the perceived E field at point P is the vector sum of the E fields of the two charges. So essentially what we have is we have that blue vector plus the red vector that's going straight downwards, and the result of this is the purple vector like this. This is going to be E net. We can say this is E right, and red could be E up. You know, the electric field caused by the upwards charge. So you can see that the E net is going towards the bottom left, the southwest, if you're thinking about compasses. So for here, the first answer that we'd have associated with the first part, I guess 14 in here, is towards the southwest, which is D. So, no solution to verify here. That's nothing to be worried about. We just know that the first one is going to be D. This is the direction of net E field. It is southwest, bottom left, whichever way you like to say it. Okay, cool. So the next part of the question is asking, what is the potential energy of the particle, of a particle charge Q that is held at point P? Okay, so now we're looking, well, we're going to have the same situation, but we're going to have, now we're trying to find the net potential energy from it. Okay, so let's talk about potential energy. Energy of charged particles. Okay, so the potential energy of charged particles is as followed. So the equation, we use the letter U often for potential and E for like the electric potential energy, because this is all coming from the electric force. So we would represent this as K, little q, big Q, just to specify that they are different charge values. Like the big Q is going to be associated with the with the top left and bottom right corners, and the little q is going to represent like the hypothetical charge that we're going to put there, and this is all divided by d, which is the separation between them. Another way that we could write k, because I know here in the option, in the multiple choice options here, they don't have the k, but k is also equal to 1 over 4 times pi times epsilon naught. Those are all just constant numbers, like we know 4 and pi, and epsilon naught is the permeability of free space, but we just know that this is like 9.09 times 10 to the 9. And it's just easier to write all of this out, but we don't actually even need to do the calculation, so don't really worry about the number. So when it's asking us, what is the potential energy of a charged particle held at point P? Well, let's think about point P. There's going to be a contribution of potential energy from the top and a contribution of potential energy from the right one right here. Okay, so when we want to add them together, we also realize that they're on corners of a square, right? So they have to be an equal distance away from them. So pretty much, when we want to find the net potential energy, so U net, this is equal to U up. So U up represents like the one with the red arrows, and this is going to be plus U right. This is the one with the blue arrows associated with it. So we find the potential energies of those individually, and then we add them together, and that will be our net potential energy as observed from a charge Q held at point P. Also keep in mind that it's positive, so it is like a repulsive thing, but we don't really need to worry about too much about signs because it's more of like a magnitude thing. Okay, so it turns out for them both, D is the same distance for their separation, and Q is the same, and the big Q is going to be the same as well, because the top left and the bottom right have the same charge of big Q. Okay, so let's write this out alongside this equation right here. So U net is equal to K Q Q over D plus K little q big Q over D. Okay, but you can see we pretty much have the same term twice, and they have to be the same because the D's are the same and the Q's are the same. So another way that we could write this is U net, the net potential energy as observed from point P, is going to be 2 times K Q big Q over D. Okay, now is that one of our options? Oh, all of our options are not written with K, are instead written with 4 pi epsilon naught. So we can write this as like 2. Instead of K, we can do 1 divided by 4 pi epsilon naught multiplied by Q, little q big Q over D. And this will be our net potential energy as observed from point P. Net potential energy. So this would correspond to one of our multiple choice options. It's going to correspond to D. So the first one was also D. The second one's going to be D as well. Cool. You see 2? Yeah, that's exactly what we got. Awesome. So we can move on to the third part of this question. The third part of this question, we got a line, and it's asking us, what is the ratio of the electric field strength at point A to the electric field strength at point B? Okay, so suppose I'm going to make the assumption that B seems to be twice as long as A. Okay, so I'll draw this out in a diagram to make this just a little bit more clear. So let's call this our line of action. Right over on the left side here, we got the charge positive Q. Okay, and somewhere along here we have point A, and somewhere along here we have point B. Okay, so the ratio of the electric field strength at point A and point B, well, we have to find the electric field strength of them individually. Okay, so actually maybe it's not great to make the assumption that it's perfectly halfway. We can give them different distance values, and then we can just have our ratio dependent on what their distance values are. So whoops, zoom back in. Let's call this distance between Q and A a nice thing that we can call that dA. Nice and reasonable for a name. And the distance between Q and B, dB. That's a nice, reasonable name. So if we want to find the ratio of their electric fields, we have to find what their individual electric fields are. So must find individual electric fields before finding ratio between them. Okay, so what's the electric field? We want to know the electric field formula, right? So this is the E field formula. We don't really need to worry too much about it being a vector because we are just like on a single line of action. But keep in mind, like if you want to do this in a 2-dimensional or even a 3-dimensional sense, you're going to need to use like vector components to it. But this equation is K, Q. I'll use big Q because that's the one of interest for here. KQ over D squared. Okay, so given this, we could do a little something like this. So for the electric field as observed from point A, well, this is going to be KQ over dA squared. For the electric field as observed from point B is going to be pretty much the same thing, except we're using dB instead of dA. Fairly straightforward. So this is KQ over dB, but you got to square it. Don't forget the squared. Okay, that's so this is for electric fields. You have to square it. Okay, so the ratio between the electric field strength of point A to point B, we're gonna want to do something like this. So ratio is going to be, we want to take the electric field strength of A and divide it by the electric field strength as observed from B. Okay, now we just got to sub the stuff in. So for EA, we have KQ over dA squared. Okay, instead of doing the division, we can just multiply it by the reciprocal. So dB over KQ, or dB squared, my bad. So this corresponds to EA. This corresponds to 1 over EB. Okay, and hey, would you look at this? You see the K on the top and the bottoms, they cancel out. We have a K upstairs and downstairs, but they neutralize each other. Same with the Q, because we were speaking in, with respect to have them having the same point charge, Q, on the line of action. They have the same Q, so that's going to cancel out on the top and bottom of here. So our final result is just going to be dB squared over dA squared. So this shall be the ratio of E field, the electric field, at points A and B. A and B. So as long as you know what those distance values are, you could just sub them into this equation and you could easily find the ratio between them. So if you find one, you could easily find the other with this little ratio here. Okay, sounds good? Sounds cool. So that would address all the questions in this, or that addresses all the questions in this little question set. So we can call this a day, or we could say, yeah, we can call this a question complete. So there is no solution to verify. Okay, cool. So the next question that we have here is, well, we have a little electric circuit full of capacitors, and we've got a couple different parts of this question. So the first part is we got to find the equivalent capacitance of all of the capacitors combined, and then the charge stored on all of the capacitors combined on that big equivalent. And then we have to find the potential, which is pretty much saying find the voltage across, or find the voltage and the charges across capacitor C1, C2, C3. So we just got to find those individually, and yeah, that would be all that we need for this. Okay, cool. So let's redraw the circuit so we can like kind of see the process and how we're going to compress all of these capacitors into a single equivalent capacitor. Okay, let me first draw out the rules and how we're going to combine them. Okay, so there are two ways that capacitors can be arranged. They will either be in parallel or in series. Okay, so, and we have to deal with them differently. So parallel capacitors add them up. Okay, so in this case, CEQ is just going to be the sum of all of the C parallels. It's kind of, and you'll see there are some similarities that we have with resistors when we go into series capacitors. These are kind of like parallel resistors. So the equivalent capacitance of series capacitors is going to be the sum of the inverse of all of the series, and then you have to invert it. Okay, so it's pretty much the same procedure that you would follow for parallel resistors. Okay, so this is the strategies. With these two rules, we can compress all of these capacitors into a single equivalent capacitor. Okay, so let's redraw the circuit and get that process started. Okay, so let's start with drawing the voltage source here. Sometimes you'll see voltage sources drawn like this. I feel like that's kind of a dangerous thing to be doing with capacitors because if you don't draw those lines at different lengths, it can be looking, it could be quite confusing or quite easily to confuse that with a capacitor. So instead, I'd recommend that you always draw your voltage sources like this, so it's impossible to confuse them with capacitors. Okay, but you got to be ready for both. It's just my recommendation is to draw them like this. Okay, so here, as you can see, we got immediately out of this voltage source, we got three branches. So we have a 2 microfarad branch. We also have a 4 that is in series with another 4. And this is C3. Okay, and another branch on this is going to be C2 and 2 microfarads. Okay, and those three branches all come together like this. And then they all lead into the next part of this node is a 3 in parallel with a 3. So this is 3 microfarads in parallel with another 3 microfarads. And this was C1. Okay, so like this. And then those two come together and then go right back to the other end of the original voltage source. Okay, this is exactly the same circuit as you see here. It's just redrawn so that it might be a little bit more clear of who's parallel and who's in series with each other. Okay, so let's draw some colored circles around here so we can kind of see who's in parallel and who's in series with each other. So let's start with a red circle here. I can see that these two are in parallel. I can see that in this green circle, these two are in series. Okay, so let's do a simplification of those parts, and then we'll get even closer, and then we can do the step again. I just don't want this to get too cluttered. Okay, so have no fear about redrawing the same circuit over and over again. It's a lot easier if you have like a drawing tablet where you can copy paste the stuff, but depending on your situation, redrawing it might be necessary. Okay, so let's do in green the CEQ of that. So we know that we got two things that are in series. So we got to follow the series formula, which is going to be 1 over the first capacitor value, which is 4 microfarads, plus another 1 over 4 microfarads, inverse that, and the result of this is going to be 2 microfarads. Anytime you do an operation like this and you have two of the same, it's going to be precisely half. Okay, so sometimes as you get more practice, you'll kind of see these rules or these little shortcuts that you can use. But try this out in your calculator. You'll definitely see that we can. You'll come to 2 microfarads. Okay, now for the red one, well, we just have 2 capacitors in parallel. That's fairly straightforward. We just do 3 microfarads plus 3 microfarads again, and with some quick maths, 6 microfarads. Nice and straightforward. Okay, you can kind of see how that works. So we can redraw the circuit with our new capacitor values, and we can we're one step closer to having a simplified total capacitance. Okay, so we had the 2 that was here, 2 microfarads. Here we had the green one, EQ. This was also 2 microfarads. those came together like that. And then the other one was untouched, but this was 2 microfarads, C2. And then those came together towards the branch that we circled in red. So that's going to be the red CEQ. And we combine that into a single capacitor that we found to be 6 microfarads. And this is our next step in our circuit. Okay, so what can we see about this? Let's we could possibly identify this section as a parallel. Parallel capacitors in this section. So let's find the equivalent capacitance of those 3 in parallel. So CEQ. Well, they're in parallel, so we're just going to add them up regularly. So it's going to be 2 microfarads plus the green 2 microfarads, and just so that the colors line up, plus another 2 microfarads. Okay, you can see how all those add up. This is equal to a solid 6 microfarads. Nice and simple. Okay, so to redraw the circuit like one last time, whoops, plus minus, that was 20 volts. 20 volts. We have a 6 microfarads. So I'll do that in blue so that we're consistent with our coloring. 6 microfarads. And then it was attached to the red 6 microfarads. Okay, and as you can see now, we can hopefully very clearly see that this is going to be a series situation. So our CEQ of our whole circuit is going to be 1 over 6 microfarads plus 1 over 6 microfarads, all inverse, and since they're the same, we know that it's just going to be half. So that's going to be 3 microfarads. Okay, so our total circuit total equivalent circuit looks a little something like this. We have a 20 volts in that is attached to 3 microfarads, and that's it. So that would address the first part of the question here, which is asking us the equivalent capacitance of all the capacitors, 3 microfarads. Hopefully we have the same answer down here. Part A, 3 microfarads, yeah. Okay. Don't worry, like this unit, like the 1/4 thing, that's supposed to be micro, like the Greek letter mu, but I guess there's just some technical issues that are not making it appear properly, but have no fear. We can still understand what it means, okay? Now, the next part of the question is asking us, what is the charge stored in the equivalent capacitor? Which is just here. Okay, so the fundamental equation that we want to use to address this situation is this. Q equals CV. Q being the charge, capacitance, voltage. Okay, so if we wanted to sub in, well, look at the numbers that we have here. We have the capacitance right there, the C value. We have our voltage, 20 volts. So this is going to be fairly straightforward. Q is going to be 3 microfarads multiplied by 20 volts. So this is going to be equal to 60 microcoulombs. Keep in mind that the micro from the 3 microfarads is going to be transferred into here. Like if you could easily convert that to a times 10 to the negative 6, and you would come to the same result. Okay, so you can see that here we have 60 microfarads. Yeah. This really means the same thing. Okay, so now that we know that we have 60 microfarads, now we want to find the potential and charges across capacitors 1, 2, and 3. Okay, so we actually want to maybe go in reverse to see the charges, because Q equals CV, that's like the big equation that we want to be focusing on to find all of these charges and voltages across the capacitors. Potential is another way of saying voltage. So a rule that I want to mention first is that all series capacitors, have the same charge. All parallel capacitors have the same voltage or potential. Same way of saying the different things. Okay, so these are the golden rules that we want to follow as we proceed. All series have the same charge, all parallel have the same voltage. And going backwards, knowing that our charge is this and our original voltage, we can quite easily retrace our steps with all of our original circuits and find our way to victory. Cool. So here we know that the charge here is going to be, not 20, it's going to be 60 microfarads. Okay, which means up here they're in series, and we know that all series capacitors need to have the same charge. So here we have Q equals 60 microfarads. Here we also have Q equals 60 microfarads. Okay, so we're going to keep breaking this down, and we know that all of these together had 6 micrograms. 6 microfarad, 60 microfarads. Okay, the bottom is still Q equals 60 microfarads, and we know on the top, all of them together are going to have 60 microfarads, but individually they're not. Okay, so first we need to find the voltage before we can find these. So for here, we know that Q equals CV, which means that Q over C is equal to V. So we want to know the voltage across the blue. So let's call that V blue is equal to 60 microfarads over 6 microcoulombs over 6 microfarads coulombs, and this will be VB is equal to 10 volts, which makes sense because we have a 20 volt source. Half of it goes into the first 6 capacitor, and then half of it goes into the second capacitor. Okay, so we know that all of these in blue all have voltage blue, which is equal to 10 volts. Okay, so to find the charge across them is going to be Q equals CV, and all of them have is equal to C, which is 2 microfarads multiplied by 10 volts. All of them have Q is equal to 20 microfarads. Microcoulombs, my bad. Don't make mistakes like that with your units. They are quite delicate and important. Okay, so here we have Q is equal to 20 microcoulombs, and the voltage is 10 volts. Okay, so that would be C2. I'm gonna write this down at the bottom here. C2. Just so we have all of our answers compiled at the end. In the same place, we had V is equal to 10 volts, and the Q associated with C2, that was equal to 20 microcoulombs. Cool. And So we can keep retracing our steps, and we can see that, okay, we have another parallel situation, and we know that these two both had the V across there. Let's call this VR for V red. This was 10 volts as well. Okay, so given that, we can find C1. So QC1 is equal to C1 over VR. Right? C over V. Q equals CV. My bad. I'm tripping. C1 V R. And we know the voltage across them is 10 volts. And the capacitance is 3 microfarads multiplied by 10 volts. It's QC1. This is equal to 30 the microcoulombs. Okay, so we can write that at the bottom as something else of our final answers of interest. C1, we had 30 microcoulombs, and it's also 10 volts. Okay, so that's C1. 10 volts, 30 microcoulombs. Cool. So all that's left here is we got to get the green. That's the last thing, because green contains C3. So we know that the Q of C3 has to be equal to the Q of C2. Right? Wait, my bad. That's not true. That's not true. We know that the voltage of across that whole series is the same as the voltage across C2. So we know that the V green is equal to V green is going to be equal to 10 volts, right? Because it's in a parallel path, and we know that the C2 has 10 volts. So since you know, the entire green has to also have 10 volts, and we know that the charge of the entire green is going to be the same. So Q green is also going to be equal to that of C of is going to be equal to QC2. And that's because like they have the exact same value. Yeah, so we know that the equivalent capacitance of C green is going to be 2. So to find the charge, we got to do Q equals C green. I'll just say CG times V, which is 10 volts. And we know that that's going to be Q is equal to 2 microfarads times 10 volts. Q is going to be equal to 20 microcoulombs. And we know that all capacitors inside all series capacitors are going to have the same charge on them. So we know that Q, the charge on C3 has to be 20 microcoulombs too. So let's write that down at the bottom. It's 20 microcoulombs, but the V value is going to be different. Okay, so we know here that Q over C is equal to V, and we know that Q is going to be we're looking for the voltage just on C3, right? And we have two things in parallel, in series. Like we have a 4 attached to a 4 in series. So the Q, we just calculated that to be 20 microcoulombs, my bad. I want to divide that by the value of the capacitance of C3, and that's going to be 4 microfarads. And this is going to give us our final voltage, which is just 5 volts. And that actually looks like a very reasonable answer because we know across this entire capacitor branch in the middle of those two series capacitors is going to be 10 volts. So only one of them, knowing that the two capacitors are identical, one of them should have half the voltage, which is 5 volts. So that makes perfect sense. So this is going to be 5 volts. Okay, and these would be our final answers for finding the potential as well as the charge on capacitors C1, C2, and C3. Okay, so yeah, that's that. So in this situation, it would be very good to keep track or to redraw the circuit many times, because as we're going back up through our process, having those intermediate circuit diagrams was very useful. Okay, so now that we have all of that, we have, yeah, all of these numbers seem to line up. It's just I've been using the prefixes, and here it's using the scientific notation, but it is all going to be the same thing. Cool, so the above solution is good. What happened? Okay, so the next question that we have on the menu today is asking us, well, along in this figure below, we got a long straight wire, the black one on the left, that has a current 4.6 amps going upwards through it. And right beside it, we have a rectangular loop which carries 9.6 amps, and I guess is going along the rectangle in like a circular type fashion, or I guess rectangular like fashion. We have the sizes of the rectangle, and we want to find the magnitude and the direction of the net force exerted on the loop as a result of the magnetic field's interaction with the two wires together. Okay, so the first thing that we want to mention is, like, why does this force even exist? So whenever we have parallel wires or parallel wires with current, going through them, will experience a force between them. Now, which direction is that force? If the currents are going opposite directions, like this, so here we have I1, here we have, in the opposite direction, I2, the force is repulsive. But if the currents are going in the same direction, they're attractive. It's kind of like, think about your friendships. You get closer to people who are going in the same direction as you. You get farther from people who are going different directions from you. We want to get closer to people who are coming along our same path, okay? That's the nice way that I use to remember this. And the equation for that force between them is like this. We have the F between the wires is going to be mu naught multiplied by current 1 multiplied by current 2, and that's all divided by 2 pi r, and you also multiply it by L. Okay, so what do these things mean? F is the force. Force between wires. Mu naught is permeability of free space. And what is this equal to? We have a numerical value. This is just like a numerical constant in the equation. So that's going to be 1.26 times 10 to the negative 6 meter per kilogram second squared ampere squared. Okay, I1 and I2 currents in wire in parallel wires. R is going to be separation between wires, and L is the length of parallelness, is the length of wires that is parallel. The key thing here is that the wires have to be parallel. If they are perpendicular, there's going to be no force. If they are like semi-parallel, like a situation like this, you would take the you need to like incorporate the angle inside of a cosine to do that. Okay, but here we have parallel wires, so we don't really particularly need to worry about that. Okay, but let's going back to the diagram, let's redraw it here with all of our numbers of interest in there. Okay, so here we have our original wire, our main wire, I guess. Here we have I1, and that is going to be how many amps? 4.6 amps. Here we have a loop where we're going to have I2 going up on that side and going down on this side. Okay, and this is going to be 9.6 amperes. Okay, then we have to have some distance values. Let's put them in red. So our distance, this distance here, that's going to be that's distance A, and A corresponds to 0.15 meters. A equals 0.15 meters. The separation here, that is C, and C corresponds to 0.10 meters. Whoa, let's chill out there. 0.10 meters. And this distance, pretty much the height of the rectangle, that is given as L, which is 0.45 meters. Okay, so essentially it is only this part and this part, only blue wires have a force. The green wires, or the green parts of the rectangle here, green is perpendicular, no force. Okay, so maybe we can call this section up and this section down, right? Because that's like it's gonna be like the direction of the current, and essentially what we want to do is we want to find the net force experienced by this rectangle, right? So the net force of the rectangle, let's call it F net, is going to be equal to the force experienced by F up That's the force experienced just by the upwards branch plus F down. Oops, not P. Okay, so the force between them, that's going to be the total net force experienced between them, because it's only going to be the up section and the down section that contribute to the net force. Okay, so let's have a calculation for F up, or write an expression for that. So we know that we have our equation up here. So we have epsilon naught times I1 times I2. Now we can leave them both as positive because they're going in the same direction. If we put them as negative, or if they're going different directions, we'll put one as negative and one as positive. Okay, so they have the same sign here, and we're going to divide that by, going back up to here, 2 pi r, but in this case r is equal to c. C being the separation between the wire that's not in the rectangle and the wire that is in the rectangle. But for the other one, we're going to be C plus A, but we'll get there when we get there. And then this is times L. And that is the entire equation. Exactly. Yeah. So this will be F up. F down is going to have a similar equation here. We're going to start it off with epsilon naught. I1 is the same, but we're going to use negative I2. This is because going down, going opposite direction, negative. Okay, because we need these forces to have different signs for this to work out properly. On the downstairs of here, we're going to have 2 times pi. Those are going to be constant and mandatory. But instead of just C, we have to do C plus A. The reason why is because, well, the down section of this square loop is more than, like, the distance between that and I1 is, is A plus C. Okay? And the length that they are parallel with is also L, so that's going to be the same here. Okay, cool. So let's incorporate these into our equation above. So F net. So instead of F up, we'll write out epsilon naught I1, I2, L over 2 pi C minus mu naught I1, I2, L over 2 pi C plus A, and we can factor this out to make our calculation a little bit easier. So we factor out everyone that's common to these two terms. So that will be epsilon naught is common to both, I1 is common to both, I2 is common to both, 2 pi on the downstairs is common to both, and L on the upstairs is common to both. And then all that is left that is different is going to be 1 over C minus 1 over C plus A. Okay, so this will be our expression for this situation, and then we can sub in some numbers and get the final result of the net force. Okay, so epsilon naught, here we have that number as 1.26 times 10 to the negative 6. We're not really going to worry about units because I trust that the algebra is all good, and the units will make this quite long to write. I1 is 4.6 amps. I2 is 9.6 amps. And, whoops. Okay, then we divide that by 2 times pi. We'll multiply that by L, and L in this case is 0.45 meters. Then 1 over C. C is 0.1. minus 1 over 0.1 meters plus, and then the distance of A, 0.15 meters. Okay, so let's do some quick math and multiply this together. Pulling out my handy dandy TI-84 calculator to do the quickest of all the maths. Okay, so 0.1 minus 0.25 inverse times 1.26 times 10 to the power of negative 6 times 4.6 times 9.6 times 0.45 divided by 2 times pi. And my calculation results for this is the net force as experienced from these two is 2.391 times 10 to the negative 5 newtons, because force is always in newtons. Or since we're using SI units, it should always be in newtons. Okay, so this will be the net force as experienced by the loop due to the straight wire. Okay, and we also want to give a direction to this. We know that we had positive forces go as attracting to each other and negative forces as repelling. So this will be to the left towards the I1 wire. Okay, so that would address this question. Did we come to the same conclusion at the end? Pretty much the same, just a little rounding thing, but otherwise the calculation is perfectly good. The solution is reasonable. Of course, they just calculated it, calculated the forces individually instead of putting them together and factoring, but we came to the same conclusion, so everything is good. So here, the above solution is good. Awesome, wasn't that fun? Okay, so this is the next question that we got on the menu today. It's actually 6 questions, but, you know, it's nothing to be worried about at all. This can still be a good, fun time, okay? Don't be worried about all these words. We just got to read them and get meaning out of them, okay? So the first question is asking us, a block is placed on a plane whose angle of inclination is 30 degrees. Pretty much what that means is like we have like a ramp like this. And this angle right here, 30 degrees. Yeah, that's what that means by a plane on an inclination. The coefficient of static friction, the coefficients of static and kinetic friction on the block of the inclined plane are both 0.2. Okay, so assuming we have a block like this, we know that our US is equal to our mu k. These are coefficients of friction, is equal to 0.2. Okay, so we want to find out pretty much how is this block going to interact with the ramp. Is it going to stay in place? Is it going to slide down? Is it going to travel up at a constant velocity? Is it going to travel down at a constant velocity? Or is it going to accelerate up? Okay, so the first things that we can disqualify is that there is no mention of anything that would cause an upwards force. The only force that appears to be the only forces that appear to be valid in this situation are friction and gravity. So friction and gravity only. Only. Impossible for block to go upwards. Okay, and another thing that we know is that constant velocity is only possible when zero net force says, or the question says that the block was placed on it, if it was put on the ramp with like an initial velocity, it would say it would be put on it with an initial velocity. So saying that it's placed on it means that it was put on with the velocity of 0. So initial velocity 0 So this actually disqualifies some of our multiple choice options. So accelerates up and travels at constant velocity. All these three disqualified. Okay, so now we just got to know, is it accelerating down the plane or is it going to stay in place? Okay, so another thing that we want to know, that we want to mention, is that how, or an easy way that we can go about this is to think about how the coefficient of friction is defined. So this is, for static friction, defined as tan theta of where theta is the angle at which the stationary block starts to slide. Okay, so maybe as a real life example of this, if I got like here I have my calculator. It's my calculator case in here. So right now you can see it's not sliding, but as I tilt it, eventually you see this cover is eventually going to start to slide. The moment that angle starts to slide, you take a measurement of the angle and you take the tan of that angle. That's going to give you the coefficient of friction. So using that process, we can take the coefficient of friction that they give us and go backwards. Okay, so if, like, maybe we can do this even higher up here. So if tan angle is equal to 0.2, because that was our given coefficient of static friction, that means theta is just the tan inverse of 0.2. Now asking my handy dandy calculator to figure that out for me is tan inverse of 0.2 is 11 degrees. 11.31 degrees. Angle where sliding starts. So the angle has to be less than 11 degrees for this to stay stationary, right? So if it's here, it's a very small angle, you're not going to slide. But when you got it really sloped up like this, more likely to slide. So we know that 30 is greater than the critical angle where it starts sliding. 30 is bigger than this. .31 degrees must be sliding at this point. And it's sliding because the frictional force is not enough to completely counteract the gravitational force. And that's why it's sliding, which means there is a net force that is not 0. And when there is an unbalanced force, or a net force more than 0, there has to be some acceleration. So that disqualifies A, which is it remains stationary. So we know that it has to be B. The block will go down the slope. Okay, was that the answer that we had here? Okay, I'm gonna just write that out real fast because that's important. part 1, block slides because angle, oops, of starting the slide is 11 degrees. Okay, cool. So that's the first part of the question. The second part of the question is a whole different situation. Okay, so I'm gonna just clear off this whiteboard just to have a little bit more space. Second part of the question is not really connected to the first, but still along the same lines. So an object of mass 5.5 kilograms is allowed to slide from rest down an inclined plane. The plane makes an angle of 30 degrees with the horizontal and is 72 meters long. The coefficient of friction between the plane and the object is 0.35. And it's trying to get us to figure out what is the speed of the object at the bottom of the plane. Okay, so let's actually draw out this situation right here. So we got a big long triangle like this. Move it down like that. And we got a block at the top that looks like this. And they said it was 5.5 kilograms. Okay, we know that the distance, the length of this thing, the entire ramp, is 72 meters. 72 meters, exactly. We know that this angle got to be 30 degrees. Okay, another thing, they gave us the coefficient of friction. It's kinetic friction, because it is sliding, is 0.35. We want to find speed of the object at the bottom. Of object at bottom. So first I'll write out our plan on how to go through this, and then we will go through the plan step by step. First we want to find net force on block. Then we want to get the work. Done on block. And then work equals kinetic energy. And isolate velocity. Okay, cool. So the first step here, we have to find the net force on the block. And we want to maybe set up, or we definitely want to set up our coordinates so that our coordinates are parallel to the slope itself. So let's say this is the positive x direction and this is the y direction. Okay, let's make a free body diagram of the block. We can just make it a point here. So we know that we have our gravitational force, and our line of action is like this. And kind of like this. So we have 30 degrees. Yeah, like that. And we have our force of friction like this, and we have a normal force like this. Y and X. Okay, so this is a free body diagram of our situation, but you know, it's just not drawn on the ramp. So this is pretty much what the block is going to be like. These are the forces that the block are going to experience. Okay, and you know, to resolve everything along the X and Y axis, we're going to need to break down mg into its X and Y components. Okay, I'll do that in a different color to kind of show how we can pull that off. So we're going to have this. Let's call that mg y, and this is added with that, mgx. Okay, so as you can see, now everything is along the lines of action of our question. And knowing this, we can get the net force on here, which is going to be straight down the ramp. And yeah, that once we have that, we're one step closer to our final answer. Cool. So we know that Fn, the normal force, has to be equal to mgy. And the reason why is because, well, if the force along the y-axis, meaning like up and down relative to the ramp, if it was non-zero, that means like the block would either be going into the ramp or it'd be flying off the ramp. That is not the case. It's always sliding along the ramp. And if we look at our coordinate system, we can see that the y value, like with this tilted coordinate system, the y value is always going to be the same. The only thing that really matters is the x, but we still need to consider our y, and we know that there's going to be zero net force along there. And the only way that there's going to be zero net force along the y-axis is if the normal force is equal in magnitude to the y component, the tilted y component of the gravitational force. Okay, so when we think about this, when we look at this, you can see it's a right angle triangle situation, and the y component is associated with cos 30. You see that? So we could write this as mg cos, cos 30. Okay, seems about reasonable. And we know what m and g are. M was given us as 5.5 kilogram. And we know that g is equal to 9.8 meters per second squared times cos 30. Let's ask our calculator to get us the answer for that. 5.5 times 9.8 times cos 30 degrees. And my calculation for that, Fn is equal to 46.679 newtons. Okay, now why do we need the normal force? Because it is a part of our calculation for the frictional force. Okay, so the next thing that we want to do is we want to take up the forces in the x direction, or in the tilted x direction, basically alongside the surface of the slope. So we know that we're going to have the x component of the gravitational force plus and the frictional force. We're not going to know what they are, so we can write this as the sum of all forces along the x direction is equal to the mass times the acceleration down the x direction. And we're trying to solve for the a value. And this is going to be the mgx. And mgx is positive because you see it's going along the positive x direction, minus force of friction. And you see force of friction is negative because it's going the opposite direction of the positive x direction. Pretty much the frictional force is going up, is towards up the slope. Okay, so another way that we can write this is max. We can write mg, the x component, instead of cos 30 is going to be sine 30. Minus the normal, frictional force is actually the normal force times the coefficient of friction. So it's going to be Fn multiplied by mu k. Okay, and this is what we want to do is now we're just going to sub in these numbers. So max. Actually, we don't need the we just need the x. We actually need the force, not the acceleration. But yeah, we can keep writing it like that. So we have 5.5 kilograms multiplied by 9.8 meters per second squared multiplied by sine 30 minus Fn, the normal force, which is 46.679 multiplied by the coefficient of friction, which is 0.35. Okay, so let's send this into my calculator to figure out what this is. That our normal force times negative 0.35 plus 5.5 times 9.8 times sine 30 degrees. And my calculation for this, Fx is equal to 10.61 newtons. Okay, awesome. Now that we have the net force, down ramp, we want to get the work done across the ramp. The work done by net force across the ramp. Across ramp. Okay, so we know that work, represented with W, is F times D. And we know that F and D are going to be parallel, so we can just multiply them regularly. And normally you do a dot product, but in a one-dimensional situation like this, it's really just multiplication. So we know that our net force is going to be 10.61 newtons. Multiply that by our distance that it is that the force is applied for, which is 72 meters in this case. Oops, not capital M, little m. So let's calculate that real fast. So our previous number times 72. And we have 764.1 joules. Joules is the unit of work, and hopefully some of you recognize that joules is also a unit of energy, which is exactly where we're going to go to next, because we know that all the work becomes kinetic energy. And we've already considered, like, we have the net force, so we don't need to consider the work done by friction because that's already incorporated into the force itself. Okay, so all of the work done by the net force is turned into kinetic energy. So we know that work is equal to kinetic energy, which is equal to 1/2 mv squared. Okay, so if we want to isolate the velocity value, we would do 2 times the work divided by mass under the root is equal to our velocity. And our velocity is what we're really after here, the speed of the object at the bottom. Okay, so let's put under the root 2 multiplied by our work value, which was 764.1 joules, divided by our mass, which is 5.5 kilogram. Okay, and let's calculate that out. 2. Well, let's get the root there first. 2 times the previous thing. Divide 5.5 under the root. Gives us 16.67 meters per second. And that would be our final answer for the second part of this question. Velocity of block at bottom of ramp. And it seems like a reasonable speed because 72 meters is quite long, and like a force of 10 newtons applied over that type of distance seems like a reasonable answer. Okay, cool. Oh, do we come to the same conclusion here? Exactly. So that's awesome for part 2. And we can move on to part 3. Okay, so I'm gonna clear this off. And okay, we can move on to part 3 of this question. So a 5 kilogram object slides down a frictionless surface inclined at an angle of 30 degrees from the horizontal. Total distance moved along by the object is 10 meters. What is the work done on the object by the normal force? Okay, so let's draw the situation. And the quick answer is 0. Whoops, that is not a slope. It's not the shape I was looking for. It's this one. Okay, so here we have a block sliding down here. We have the normal force is going here, right? It's got a right angle to here, and the block is traveling this way. There is no work done by the normal force because work is the force that is parallel to the movement. So work only occurs when the force is parallel to the direction of travel. Okay, the normal force is completely perpendicular to the direction of travel, so there is no contribution of the normal force, or the normal force does not do any work on the block as it's sliding down here, because, well, you're going the other direction and you're not moving it in that direction. It's not working out. A nice way that I can think about this is like, imagine yourself pushing around a shopping cart. When you're pushing around a shopping cart, there's still a gravitational force on the shopping cart, and the gravitational force is going down and you're pushing it, like, you know, horizontally. Gravity is not doing any work for you. It's always going down, but it's you that's pushing it around. You are the only one that's providing a force in the same direction as the shopping cart. There is a gravitational force, but it's not doing any work. The work done is only when the force, you know, in the shopping cart example, it's you pushing the cart. Only when the force is in the same direction as the travel of the object, that's the only time the work happens. Okay, so perpendicular forces, 0 work, doesn't work out, and yeah, so that would be yeah, no work. Awesome. So that concludes part 3. Now part 4 is a little bit of a different situation. Okay, let's clear that off. So part 4 is asking us, a mass of 2.5 kilogram is sliding along a table, a frictionless table, with an initial speed of v, and we don't know what v is. I think we're gonna need to calculate v. When it strikes a spring, all this and the force constant of the spring is 500 newtons per meter. It compresses by a distance of 5 centimeters. So now knowing that, we have to calculate the initial speed of the block. Okay, so let's write out our given information. We know that the mass of the block is equal to 2.5 kilograms. That's about 5 pounds, maybe a little bit more. We know that the spring constant, 500 newtons per meter. We know that the compressed distance, I prefer to write it as delta x, because like x is typically for like a particular distance and delta is like the change in distance, really measuring like the amount that is compressed. So I prefer to use delta x, but if you just use regular x, just make sure you keep it straight in your head that it's you know, it's going to be a compression. And here we have 5 centimeters. But to make this a little bit easier for our calculations, we can write 5 times 10 to the negative 2 meters. And that is 0.05 meters. Okay, just was a little bit easier to calculate. And actually that's all the information that we really need to know about this situation. So we know that initially the total energy in this system is constant. Initially, all energy is kinetic energy in the moving block. All of that energy, all of that kinetic energy, all that kenergy is then, let's transformed into spring potential energy. Okay, so when basically what's happening is the sliding block slides, and as it hits the spring, it's slowing down. And once it is going to momentarily have a velocity of 0, no kinetic energy at that point, and at that point it's going to slide back, and the spring is going to recoil and push it back outwards. So pretty much what we want to have is U spring, U meaning potential energy, potential, that's the way I remember it, is going to be equal to the max kinetic energy of the whole thing. Okay, so we know that we can write out these equations for potential energy of a spring. We know that there is 1/2 k delta x squared, and this is equal to its kinetic energy initially, which is 1/2 mv squared. We're trying to isolate v for velocity. So to do that, well, we can multiply both sides by, or let's just send everything to the left side. We can have like v squared is equal to k delta x squared over m, and put that all under the root. So v is equal to under the root k times delta x squared over m, all under the root. Okay, now let's sub in our numbers for this and we can be happy. So k is equal to 500 newtons per meter. It's a pretty strong spring, gotta say. Compressed by 5 centimeters, so that is 0.05 meters. That's gotta be squared. That's all divided by the mass, which was 2.5 kilograms. Wow, I really just did memorize that. Awesome. Okay, cool. So let's ask our old calculator, what is the result of this calculation? So, under the root, we shall have 500 multiplied 0.05 squared, divide by 2.5, all of that under the root. We get our velocity is 0.71 meters per second. Okay, so that would be our initial velocity of the block. Do we have the same calculation here? Yeah, we do. Awesome. So this is based on the law of the conservation of energy, and given that, we're good. We're groovy. Cool. So that wraps up part 4 of this very long question. However, we gotta keep it moving till the finish line. We ain't done until we done. So the next part of this question is the graph. This graph right here shows the position of a particle, and it depends on time. What is the closest to the instantaneous speed of the particle at t equals 3 seconds? So that's about here. And pretty much what we want to do here is we want to analyze the slope at this point is going to be pretty much what we want to find the slope at time equals 3 right here. So slope at t equals 3 will give us the instantaneous velocity. Okay, so looking at the slope, it's not quite easy for me to like put like a ruler on the screen, but if you were to put a ruler on the screen at like time equals 3, you would see that it definitely looks less steep than 1 like 1 would be like, you know, if you draw a line from like x equals y, that straight line is more steep than this. So by observation, must be less than 1 because the slope is flatter than a 45-degree line. Okay, so that's instantly going to disqualify D and E. Okay, so next we want to look around the neighborhood of 3, and you can see, hey, if we go like to the right, to the left by 1, and to the right by 1, you can see like as you traverse 2 seconds from t equals 2 to t equals 4, you're going up by just under 1. So that actually kind of corresponds to a slope of around 0.5. So should be around 0.5 because from t equals 2 to t equals 4, there is a increase of, honestly, it's just less than 1. And I know that it's just less than 1 because at t equals 2, it seems closer to the line above it than it does at t equals 4. Okay, which means that since it's just less than 1, must be less than 0.5. If we observe that like it was closer to the line above it at time equals 4 than it was at time equals 2, we would know that it must be like just above 0.5. But since we know that it has to be less than 0.5, and there's only one option that's less than 0.5, which is still pretty close to 0.5, which must be 0.4 meters per second squared. So this would be our best guess for the instantaneous velocity at time equals 3. Okay, so hopefully we have a similar conclusion here. Yep, correct answer is A. Yeah, and I guess I did take some numbers from there, but you don't really need to do the calculation if you're just good at observing stuff. So just look at the immediate neighbors of it and help calculate it that way. And yeah, so we know that it must be answer A, just based on the things that we looked at. And if you're doing this in real life, like this would probably be printed out on a paper. Honestly, just like take a ruler, stick it on your paper, and just try to draw a line of best fit at around t equals 3, and then try to find the slope of that line. See who lines up closest to it. All right. Cool. So that wraps up the 5th part of this hexadecimal question, hexa 6-term question. And okay, so the next part of the question is asking us, I guess in a completely unrelated to all the other parts of the question, is asking us calculate the work done by the force 2x I along the path 0, 0 to this point, which is 2, 0, to the next point, 2, 2. Okay, so our force is like this. So we have 2x I plus 0j. Okay, so this is our force. I know the question doesn't write 0j, but we know that there is, because we don't have a written y component of this force, it has to be a 0 y component. I'm just writing it out explicitly so that when we do the cross products, it's going to be, the dot products is going to make a lot of sense. Okay, so it's looking for the work done from 0, 0 to 2, 0, and then from 2, 0 until 2, 2. Okay, so let's call this path 1. Let's call this path 2. So we want to pretty much just find the work total is equal to the work of path 1 plus the work done of path 2. So to find the work, we know that work is equal to the force. Oh, that's a vector force. Dot product the distance, the vector distance between the 2 points. Okay, so for path 1, we know that, well, our first force vector is just going to be 2x in the I direction plus a 0 in the j direction. Cross product with, now we have to find the distance between them, between point 1 and point 2. So pretty much what you do here is like 2 minus 0 in the I direction plus 0 minus 0 in the j direction. Okay. Distance vector from origin to P1. Always do destination minus start. Okay, so let's just call that P1. So the cross product of this is going to be 2x times 2 plus 0 times 0. I know we don't strictly need to write that, but just be formal with the dot product definition. It's going to be like this. So the result of work from path 1, well, that's just going to be 4x. Okay, so that's the first part of our stuff. The second thing that we need to do is the work done on path 2. And we know that it's going to be the same dot product, or it's going to be a similar dot product, but we have a different distance vector. So we have 2x I, the same force, right? Yeah, it's all the force is going to be constant throughout this whole situation, plus 0j. And we dot product that with, now our starting point is 2, 2. So it's going to be 2 minus 2 in the I direction. And this is going to be plus 2 minus 0. Whoops, let's make that 2 a little bit more pretty. 2 minus 0 in the j direction. So here is P1 to P2 to 0 until 2, 2. Okay, and as you can see, this would just be 2 in the y component. So the calculation of this is going to be del path 2 is equal to 2x multiplied by, well, 0 plus 0 multiplied by 2, and this is just going to be equal to 0. Okay, and this makes perfect sense because the displacement was purely in the y direction and the force is purely in the x direction. When the work and the force are perpendicular, or I mean when the force and the distance that it travels are perpendicular to each other, there is no work in response to that. Okay, so we have our work from path 1 and our work from path 2. We know that our work net total is going to be equal to them added up. So it's going to be 4x plus 0. So it's just going to be 4x. Okay, so that's going to be our total work. Awesome. Hopefully we have the same conclusion here. Yeah, it's going to be 4x. And all that's left is to mention is that the total force would be the sum of there. Yeah, cool. So this solution is pretty good. So that is part 6. Yep. The total force as sum work of the should be shown. Otherwise, all good. Awesome. That's a very long question. Okay, so the next question that we have on the menu today is giving us this diagram. And with this diagram, the guy wires, I think it means the guide wires, used to support this telephone pole are, I guess, as they are in this diagram. So we want to get the force in each one of these guide wires, FP and FA, and we want to get them in Cartesian vector form. This is a fairly straightforward question. So we know that to get Cartesian vector form, the vector form like that, we would just take the vector magnitude, and we are given the magnitudes in this case, multiplied by the unit vector along the path. And the unit vector of the path is just equal to the distance vector divided by the magnitude of the distance vector. Okay, so this is our procedure and how we want to proceed. Okay, so let's start with getting the Cartesian form of force A. Okay, so force A, the magnitude of force A, magnitude is often represented with absolute values. Sometimes you also see it with double absolute values so that we don't get it confused, because there can be negatives in there that you don't treat. This is just to show, but stay ready for both of these notations, and that will be equal to 250 newtons. And we know that force A acts along the path point A to point C. Okay, so now we want to have a let's get our points of interest. So A is at this point. Okay, so let's look at the diagram. A is 0 in the x direction. It's directly above the xy intersection, but it is 4 meters in the z direction. Okay, so we have 0, 0, positive 4 meters. Okay, now the point C, it has 0 in the x, a 0 x component. It does have a y component though, and that y component is, oh my bad, it does have an x component. Has an x component of 1 meter. Okay, you see right here, hopefully you can see my mouse. Right, you see my mouse right here, 1 meter right there, towards the bottom right here. I also show that the y component, the x component is negative 1 meter. Oh, that's another big thing, negative 1 meter. The y component, it is 4 meters away from the x-axis. That's 4 meters for this. And its z component, well, it's on the ground, so its z component got to be 0. Okay, so given this, we want to find the distance vector AC, and to do that, we're just going to have AX minus CX. Whoops, other way around. We always want to do destination minus source. So CX minus AX in the I direction, plus CY minus AY in the J direction, and plus CZ minus AZ in the K direction. So remember, when you're doing position vectors, do the destination minus source. Okay, so given that this is what we got for our AC, let's put in our values. So our x value for C is going to be -1 minus the x value for A, that's 0. That's in the I direction, plus, now the CY is 4, and the A is 0, so that's going to be that. And the Z components, well, our C is 0, and our A value is 4, and this will be in the K direction. So our AC is going to be a -1I plus 4J minus 4K. And all of these are in meters. Okay, and that looks kind of reasonable. If you wanted to go from point A to point C, you would go -1 in the X direction, you would go +4 in the Y direction, and -4 in the Z direction. That looks perfectly reasonable. Cool. So given this, we need to find the magnitude of this to get our unit vector. Need magnitude for a unit vector. Cool. So in order to do that, our AC, it's going to be pretty much a Pythagoras type of operation. So it's going to be -1 squared plus 4 squared plus -4 squared. So this is how you get the magnitude. So this is the X component, the Y component, and the Z component. You sum up all of their squares, put them under the root. So we have, pulling out my calculator for this one, we got the square root of 1 plus 16, which is 4 squared, plus 16 once again. And that's going to give us a value of 5.745 meters. Okay, so if we want to get our unit vector for AC, we would just do our RAC vector divided by the magnitude of RAC. Okay, and our RAC vector was originally -1 in the J plus 4, whoops, that's not in the J, that's in the I, like that, plus 4 in the J minus 4 in the K direction, all divided by 5.745. Okay, so we're just gonna multiply or divide all of those terms by 5.75 times 1. So this will be equal to 0.1741 in the J direction. Not the J direction, the I direction, my bad. And that's negative, plus 0.6963 in the J direction, minus, and it's going to be the same for this one, so it's going to be 0.6963 in the K direction. Okay, so this is our unit vector. Unit vector for AC. Now, to get the force AC, we just have to do the magnitude of AC force multiplied by the unit vector of AC. Okay, or I guess it's not really AC, it's just A, but it is pretty much the same thing. Now, in this case, that's just going to be that is going to be 250 Newton multiplied by negative 0.1741 in the I plus 0.6963 in the J minus 0.6963 in the K. Okay, so let's do that math real fast. This times 250. So here we're going to have 43, negative 43.52 in the I direction plus 174.08 in the J direction minus 174.08 in the K direction. And this will all be in newtons. This shall be our Cartesian form of a vector or a force in guide cable. Awesome. So this will be one part of our solution. Hopefully we have an agreeing answer here. And 43, 174, 174 looks good. Just some rounding errors, but that's nothing really to be too worried about. Now, okay, so that's good. Now, just to save a little space here, now we will do the same thing, the same procedure for the other cable. Okay, so now we want to do it for the B cable. So we want to first find, we want to get RBD, then we want to get UBD, and then once we have that, we get FBD. Okay, so this is our order of operations that we want to proceed with. Okay, so let's identify our points of interest. So point B on the pole is in the X direction 0, in the Y direction is 0. Right? It's just like straight elevated from the ground. And then its height is 4 meters plus 1.5 meters. So that is 5.5 meters. Okay, now point D, want to get that point of interest. That is positive 2 in the X direction. Hopefully you can see that. It's just above the D right here. So that is 2 meters in the X direction. Then we have negative 3 meters in the Y direction. And then we have 0 meters in the Z direction because, well, it's simply on the ground. And Z is the height. Okay, so to get RBD, we shall do the destination minus the source in all of them. So we will have 2 minus 0 in the I direction, plus the destination is negative 3, where the start is at 0, minus 0, in the J direction, plus the destination is 0, minus the source, 5.5, in the K direction. RBD. Okay, so we'll have 2I minus 3J minus 5.5K, all in meters. Okay, now we can quickly get the magnitude of RBD. Going much faster now as opposed to than I was the first time because well, things should be easier the second time around. Plus negative 5.5 squared. So RBD, the magnitude is going to be Okay. Under the root, we're going to have 4 plus 9 plus 5.5 squared. This is going to be 6.576 meters. Okay, now we got to find the unit vector for BD. It's just going to be RBD vector divided by magnitude RBD, which is going to be 2I minus 3J minus 5.5K over 6.576. Okay, UBD, this is going to be equal to 2 divided by 6.576 is 0.30401 in the I direction minus 0.4562 in the J direction minus 0.8363 in the K direction. Okay, so this shall be our unit vector for BD. And we know that FBD, which is the force inside the cable, is going to be equal to our FB value, magnitude, multiplied by UBD. So that's going to be, reading from the diagram, the force magnitude in B is going to be 175 newtons multiplied by 0.3041 I minus 0.4562 J minus 0.8363 K. Okay, so doing these calculations super fast. FBD, whoops, not BB, BD times 175. The first one is going to be 53.2 I minus, this time is 175, 79.8 in the J direction minus 0.8363 times 175. This will give us 146.4 in the K direction. And this will be newtons. And this will be the force in cable B to D. Okay? So hopefully we have a calculation in the solution here that agrees with that. So for the second one is going to be 53, 79, 146. Awesome. So yeah, that would be the force in the other wire. Just a little bit of rounding discrepancies, but otherwise it's well within reason of just like being in a rounding error. Okay, so yeah, the above solution is good, and as you can see, the process will always lead us to the right place, and the stuff's pretty fun, can't lie. I enjoy it. So the above solution is good. Awesome. Oh man, that was the last question. Time flies when you're having fun, as the old saying goes. So those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you would like to submit your own questions, please visit the links in the description, and remember to leave a like and a comment if you enjoyed the video. If you really enjoyed the video, share this video with your friends. And this has been Millan from OneClass. I hope to see you again soon. Take care, have an amazing day, and remember, physics is always a fun time. Never forget it. Take care, have a great day.